So my name's Dan Nadeau. I'm an application engineer here at Saratech. My expertise is Femap, SimCenter 3D, SimCenter NASTRAN, and XCAD. And a picture of me in the top left corner. A lot of people are working from home now, so hopefully that's going pretty smoothly for you. In the bottom right, I have a picture of a disc golf basket. It's something I like to do when I have my free time. Get outside, enjoy the outdoors. All right, so today what I want to talk about is MPCs inside of Femap. So, what are MPCs? Just to give a brief background. And the common MPCs that are used are RBE2s and RBE3 elements. So I'm going to discuss the differences, why you choose one over the other, and just an overview of them. And then I'm going to go ahead and go over to Femap and give a couple demo models, use cases. I think the demo models really help show the difference between an RBE2 and an RBE3 element. And the reason for this webinar is that, from teaching classes and doing project work and just talking to my clients, this is a question that comes up pretty often, which element type should I use, and what's a good application here, and am I using it correctly? All right. So NASTRAN has two types of constraints. The first one is a SPC, or single point constraint. The second one is an MPC, a multi-point constraint. So single point constraint is applied to a single grid point or node, and with that you can enforce zero or non-zero displacement. So you could apply a we'll just say a enforced displacement. So you want the node to move a value, or you can say this node is not allowed to move a value. MPCs are called multi-point constraints. So a multi-point constraint is a mathematical constraint relationship between one grid point and another grid point, or a set of grid points. MPCs are difficult to write. So NASTRAN or SimCenter NASTRAN now created these element types called rigid elements, which internally create MPC equations. Femap supports 4 rigid element types: RBE1, 2, and 3, and R-spline. The most common ones are RBE2 and RBE3. Now, these are not actually true elements since they do not modify the stiffness matrix. They just constrain displacements of one grid point to one or more other grid points. So I even bolded this. So the motion of a degree of freedom is dependent on the motion of at least one other degree of freedom. This is a displacement, not an elastic relationship. It's not dictated by stiffness, mass, or force, and it's a linear relationship. So that means it's in small displacement theory. So if you are using something with large displacement, such as a nonlinear analysis, just be, I guess, careful around rigid elements. A common error that you'll notice is this double dependency. NASTRAN will yell at you if you have something that is dependent on something else. So a dependent degree of freedom cannot have a displacement that's relative to another grid point and have that value described in an SPC. So more information on MPCs and rigid elements. Some of the information that I have in this slide comes from the NASTRAN User's Guide, Chapter 9. And there's also more information in the theoretical manual as well. So I actually, we'll go quickly here into Femap. To how we get to that User's Guide, you can just say help SimCenter NASTRAN. And then from here, you can go ahead and open up your SimCenter NASTRAN User's Guide. And over here, we can filter it under constraints. And you'll see right here some of the information that I have. So here's an overview of constraint, and it's basically saying you can have a single point constraint or a multi-point constraint, which is what I discussed earlier. Now, as you slide through this user's guide, there's some information on single points SPCs. And then as I scroll down, there's some information that's related to MPCs as well. It should be here shortly. Enforced displacements. There we go, multi-point constraints. All right, so a lot of the things that I'm going to mention are found in here, and if you want to read more, this is where you would find it in the NASTRAN User's Guide. Okay. Now, how do you create MPCs inside of Femap? It's under the constraint. You see that you would right-click on your constraint definition and you can specify equation. You can also do from the pull-down window model constraint equation, and that will bring up this box that's shown right here. All right, when you create a constraint equation, you must specify all these terms as shown in this equation down here below. So you would specify your title, your palette if you want to change it, the node that you're specifying, and those degrees of freedom, and that would add it down here to your equation. And I even put a note, the first term entered is the dependent term. So here's an example of why one would go ahead and manually create an MPC equation. So this could be used for random analysis. So in this instance, I have an electrical box with some sort of components inside, and I want to make sure that those components are not hitting the physical box. So I need to compare relative displacements or relative motion. So in my example, grid point 1 is in the middle here, is my new output. So it's just a node that's located in space that's not relative. Well, that's not, it's a new node, so it's not attached to the structure, I guess we'll say that. Grid point 2 is location 1, and grid point 3 is location 2 as a subtraction. So I'm going to find out the relative displacement between node 3 and 2. Now, since MPCs are difficult to write, we have these things called rigid elements. So the first one that we're going to talk about is an RBE2 element. You can create a rigid element by going to Model Element, and then from there you go ahead and you specify dependent and independent nodes. Now, there are degrees of freedom. As you see, you have 1 through 6 that you can specify for that dependent node. Now, for an RBE2 element, we'll dive deeper into this as we go. So the dependent nodes are related 1 to 1 with the independent node in each connected degree of freedom. So for example, if the independent node is displaced 1 unit, then all the dependent nodes will also be displaced 1 unit. So think of an RBE2 as an infinitely rigid element. So if the independent node is displaced 1 unit, then all the other ones will also be displaced 1 unit. So they're rigidly connected. All right. So here's just some general information about RBE2 elements. So it connects one independent node to any number of dependent nodes, and then we need to specify at least 1 degree of freedom. So you need to lock down any one of those 6 degrees of freedom. Now, what I really wanted to show on this is if you have RBE2 elements, you can specify a thermal expansion. Normally, you want to set the CTE to match that material. And when we open up our demo model, I'll show you where you can go ahead and enter in your CTE values. Now, you need to go ahead and change a bulk data option if you want to include this thermal expansion, and I'll show that when we get there. The next element type is an RBE3 element. And you'll notice the dependent and independent nodes have switched sides of this equation now. Well, in this form, we'll say that. So now you have a single dependent node, and you can have 1 or more independent nodes with those 6 degrees of freedom allowed or unallowed. All right. A reference node, interpolation factor, and 1 or more independent nodes must be specified. Now, the big difference here when we specify an RBE3, and I'll read this definition, is the reference grid moves by a weighted average of the motion of the independent nodes rather than a rigid set. So in RBE2, they moved rigidly, and this one moves by a weighted average. So this is what they call an interpolation element. So it is not infinitely rigid like an RBE2 element. Things to consider when you are doing an RBE3 element. Be careful with rotational degrees of freedom. for those independent nodes or independent node. Most of the time, you will not want to have rotational degrees of freedom checked. And I will show an example and hopefully go over why you might want to do this, because sometimes it over constrains the model. So here's two simple examples of why one would use an RBE2 or an RBE3, and I think the demo models will also explain some use cases here. So RBE2s can be used to join to similar meshes, to connect something like shell elements to solids, beam elements to plates, and you can connect, say you have a bunch of bolted connections that are bolted to a table and you're doing some dynamic analysis. This is a common thing to do, is constrain all those together with one rigid element to one central location, so you can load the structure at the base of where the structure is bolted to, let's say, a shaker table. RBE3s are useful to put distributed load without increasing stiffness. An example here is we have some sort of mass of the object that we want to put into the structure, but we don't want to include the stiffness of that object itself. So maybe in this picture up here, there's some mass sitting in space, and that's just, I don't know, we'll just say a battery. And the battery's sitting on the circuit board. So we want to put the mass of the battery into the circuit board, but we don't want to model the battery itself. So using an RBE3 element will distribute that mass over the area where that entity would be connected to the structure without increasing the stiffness of that object.
Hey, Dan. We actually have a question from the audience.
Yep.
And the question is, can you explain why RBE3 has a DOF for both the dependent and independent nodes?
And an RBE2 doesn't? Yes. So here's the question. So in an RBE3, you see that the dependent node has degree of freedoms for all 6 in both independent and dependent, where an RBE2 only has the values for the dependent node. I believe that's just how the equation writes out, because the RBE2 element is infinitely rigid. So it's linked 1-to-1 to the dependent degrees of freedom, and it doesn't have an average value here. I'll have to double check if what the guide officially says there, but based on what as I understand it, that's how I would look at it.
Okay, great, thank you.
All right, and I mentioned earlier about this double dependency common error. And yeah, okay, I did have a picture from the FO6 file, and it says a MPC entry, a rigid element entry, lists the same dependent grid point more than once. So if this happens, there's a custom tool. It's custom tools model query multi-dependent rigid check. And from there, it'll go ahead and list for you the entities that are redundant, and then you can go ahead and fix them. A command that I use a decent amount if you have entities that are sharing a close proximity, or you want to connect them with an MPC and do a lot at a time, is under mesh connect. So inside here, there's closest link. You choose 2 sets of nodes, and it will generate line elements, constraint equations, or rigid elements between them. Multiple is the same, except you individually select your pair of nodes. You don't specify a row of nodes, if you will. Unzip will pull coincident nodes apart, and while you pull them apart, you have the ability to create line elements between them. Coincident link is if you have unzipped nodes, so nodes that are coincident, you can go ahead and connect them with a line element right there on the fly. And then rigid, it allows you to, we'll say, graphically unselect legs of a rigid element, or add legs to a rigid element. It's more like a graphical picking method using that rigid. And I should be able to show that. All right, so let's let's go over here into Femap and show some of these things. I think they demo better to help explain. I think once you see these type of elements in action, we can go from there. So in this example, I have a simple, let's say table, and I have some mass sitting in space, and I have that connected with an RBE2 and an RBE3. Now in the newer releases of Femap, now they put little icons that let you tell the independent nodes. So under view options element rigid, you can turn off that symbol. It is, I think, on by default now. So this example, I'm going to go ahead and load it, and we'll turn on a contour plot. Now, I hope this shows, helps explain what's going on between these two. So on the left, I have an RBE2 element, and on the right, I have an RBE3 element. So I'm just going to hide those really quick. And what you'll notice is the one on the left, rigid, it leaves this square patch. And on the right, it leaves not a square patch. It's pushed down more in the middle, but it's being distributed more. So a good way that I think about if you have mass attached to the structure with a MPC, so in this case an RBE2, it's as if the box was sitting on the table because the displacements are linked one-to-one. Where over here, it's acting as an average, or more like somebody put some slime on the table. So the slime is pushing its way from the center out. So hope that shows a little bit of what's going on and the difference. This one's moving as one entity, and it's moving in that plane directly down, and it's staying square because that is infinitely rigid mass into the structure. Another example, I have a rigid element on the top and the bottom. One's an RBE2 and one's an RBE3. I hope after I show them being loaded, you should be able to tell the difference. Let me turn off those labels real quick. So I have 50 pounds pushing to the right, and I have it constrained on one side. Let's go ahead and look at these results. So once I solve it, you notice that the top one remains circular as it moves over, and then the one on the bottom has become ovalized. So in this case, I'm going to look at a free body diagram. To get free body information out for MPCs, under your output requests, you must check on equation force. Then you'll have MPC free body information. So I believe I have a free body set up. Yeah, I can turn it on. So you'll notice under the RBE3, I have my 50 pounds. And each one, I guess there's 10 connections, is giving me 5 pounds split up between those 10 nodes, where the RBE2 is giving me different values. I don't know how clear you can see that. Maybe this will help. Yeah, maybe that helps. So there we go. So you'll see I have a different values, but the displacements are moving as one. Okay. So now, for instance, this is weighted average. I'm going to go ahead and move that center node. So I'll say modify, move by node. I'll move the top one and the bottom one. And I'll move them along a vector, and I'll say where they're at, and I'll specify at that same location, but go up in the Y direction, 1/4 of an inch. So that's not very much. So I'll do that again. I'll move it up some more. So we'll go up a little bit more. All right, it moved up some. It's not in the middle, but it's okay for my instance. All right, so now I'm going to go ahead and solve it again, just so we can look at the difference of the free body diagram if this node is no longer in the center. All right, so now I have my results. And if we go ahead and look at displacement again, notice we still have our entities staying together. Maybe this helps show it. And this one's still ovalized, but you'll notice that my reaction forces are not equal because the center has now moved up. So the length of the legs got a little shorter over here and a little longer over here. But in the middle, it still was halfway between each side. So that's why this load is the same as it was before, where this load on this half of the circle has increased a little bit, and this one has decreased a little bit. And here's another one that should show very similar to what we were just looking at. Is I have a simple line element that's connected down with a load, and one's in the middle and one's offset. Let me go ahead and turn this view off. All right, so let's look at our results. And now you'll notice that up at the top, this is, and of course this is exaggerated. You'll notice that this is moving uniformly, and this one's moving a little different, not quite uniform now that it's offset, where both of the ones on the bottom look to be all but identical. And again, I think a free body diagram is pretty powerful in showing what's going on. So you'll see 10 pounds is going down, and each one of these legs is equal to 1. Now, down here I have 10 going down, and the total of these legs is the 5 on each side. And now I have 10 going down, and I have 8 and 1.7. Now, to help, I guess, show or explain this, under Custom Tools, Element Update, there's choose separate colors for RBE2s and RBE3s. So I can select an RBE2 color, give them red, and an RBE3 color, and I'll give it blue. So now you'll be able to tell, and it should be pretty obvious when I was showing the results, is the RBE3 elements are not acting rigid like the RBE2 elements are. All right, so yeah, we're looking okay on time. All right, so I have a model, and I have a plate and a beam. So I want to connect them, and in this case, just, they're basically the same. It's just I want to connect them together. One's a 2D, one's a 1D entity, and I want to show the difference between setting this with an RBE2 and RBE3. So first thing, model element, and I'll hit my type, and I'll hit rigid. Now I'm going to keep all 6 degrees of freedom locked. I'm going to put the independent node at the middle, and now I'm going to select all the nodes around this rim, and I'm going to say method on curve to help me select these easily. Now I have an RBE2 element, and I'm going to do the same thing for the square. And I'm just selecting elements. Okay, so now these are connected with an RBE2 element to each one of these nodes. So that would be an infinitely rigid connection. And I can go ahead and solve this model. I think I have it set up. Yep. It should take a second, and I can look at my results. So I have, displacements turned on, and I have my elemental stresses. So seems like the interaction's working pretty good. It's working how I want. Now I'm going to delete these elements, and I'm going to set it up with an RBE3 element. And the result, I'm going to keep the results. So I'll say again, model element, and this time I'm going to do an RBE3 element, and I'm going to keep the rotational degrees of freedom. I'm doing this wrong on purpose. And now I'm going to select the nodes, say method on curve, makes it easier for me to select them. Same thing over here. And oh, this I made it all in. There we go. Select these entities. There we go. Now those are locked down, and I can go ahead and solve this solution. And just for reference, this came out to what, like 30 KSI. So I'm going to rename this. If you need to rename anything, it's just a slow double click. And I'll just call this RBE3 back. And when we look at the results, you notice that it goes to 400, it goes 10 times as high in my stress results. And if we look at deflection, it looks like it's not going into the structure. So if I hide my geometry, you notice all the high values are right here on the edge, and it's not even going to the constraint. So it's not, the load path isn't really working correctly. So it's being over constrained somewhere in here. So the issue was that we had those RBE3 elements, rotational degrees of freedom. So I'm going to go back, say modify, edit element, and I'm going to grab this element. Now I see this happen a lot. If you select an entity in here, so I'm going to hold down shift and grab them all, and you uncheck these boxes, it doesn't update. You have to specify the entities, then hit update and uncheck their degrees of freedom. And you'll notice in this box, it will now no longer show those R, X, Y, and Z. See, now they're blank. So that is how you must update them. So be careful on that and make sure that you don't miss that. So select the entities that you want, hit update, and then you can release those degrees of freedom. And now I'm going to go ahead and solve this with that new change. All right, so now when we look at our results, you notice I'm a little higher than I was before, but I'm close, and it's working its way through the structure. You can tell right here. The reason why I did this as a circle and a square is that you'll notice that the load is being transferred a little bit different between here's the RBE3 picture and here's the RBE2 picture, because this is infinitely rigid, and remember it's going to stay the same shape. Where this one, it's relative, a weighted average based on the length of the legs, and it's a little bit longer to go ahead and get to the corner than it is to get to the side of the square here. So that's important thing to notice is when you are doing these examples, make sure that you are wary of those rotational degrees of freedom. This example, I have this this rack that I have some mass sitting on here, and maybe the whole piece sits up here, and I have the top of the board up here. I have my entity in the model, and then I created a node. It doesn't need to be between them, but in this case, I'm running random analysis, and I want to know if this mass hits this board. So what I did was I created a MPC, and that's under constraints. And right here's my relative displacement, and I just went here and hit equation. And then you would specify the degrees of freedom that you are interested in. In this case, I think I had too many degrees of freedom, and it auto SPC'd out and caused some issues. So you might want to maybe remove some of those degrees of freedom. You would actually have to do that. There we go. So now in the TX, if I'm interested in TX, probably TZ is what I actually wanted there. But that's okay. We'll just assume it's Z, or we'll just hide this and we'll say it's in a different coordinate system. And now I will be able to tell the relative displacement to know if this item is going to hit this item in my random analysis. And for post-processing, you do have the ability to to plot, maybe I'm interested in T3 translation. I'll be able to plot this as like a contour arrow plot. I don't want the form there, undeformed. Contour arrow plot to see what's going on. Not section cut, contour arrow. There we go. So now I have an arrow that's showing me the displacement of that entity. So now I have it available to post-process it if I'm interested in. So now I have relative displacement of that node. And then the last demo model I want to show is I have a plate. One's on top of another. One is on top of another but coincident. And one's on top of another but merged. So under your mesh connect closest link, you select nodes to generate from. So you specify, I'll just say these first 3 nodes. And then you say 2, and you specify another row of nodes. I could do this whole side or whatever. And now I can automatically create rigid elements and connect whatever degrees of freedom I wanted. And I can hit OK. And it'll automatically create a one-to-one connection between them. Now, and the cool thing is under that mesh connect, mesh connect, there is multiple, which is what we were doing before. You specify degrees of freedom, but now you just specify one-to-one each time instead of doing a bunch of, I could have done like an entire row at once. So that's the difference between them. The next one is mesh connect unzip. So I think I have coincident elements on here. So these nodes have been merged. So I'm going to say method on surface, grab one side, method on surface, grab the other side. I forget what I selected first time. And now I can create rigid elements between them or springs. I'll just put spring damper in this case, a C bush. And now in between those connections, they have now been popped apart and there's a spring between them. And then the last one is mesh connect. I think, what did I do last time? Unzip? Yeah, so unzip pulls them apart if they were merged, where closest link will find nodes that are coincident, within a value. So 8. And now you can find a tolerance. And then same thing, I can create rigid elements between them. So anything that's within my tolerance of coincident, I can create those rigid connections between them if they were within whatever tolerance that I specified. So hopefully in my demo models and my brief introduction to MPCs, I explained, what they are, how to create them, the differences between an RBE2 and RBE3, and some applications where you would use them. And then I went through and showed you some of those demo models to help drive down use cases and the difference between them. So I appreciate your time, and I'll kick it back over. Thank you.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.